All right, if you're here and listening and you can hear me and you can type in the chat, it's quite useful if you just say whether you can hear me and the audio is okay. If you can type. If you don't have an account, then you can't type. Yeah, thanks, Henry. All right, welcome back, everyone. Thanks for following along. So we're now in the second lecture of this taught center course for exponential asymptotics for the physical sciences. And the first lecture we covered motivation for this subject, and I tried to explain to you why looking at exponentially small phenomena is both interesting and relevant to certain problems. We're going to see a lot more physical applications as the course goes, but for the next couple lectures, we're mainly going to go into the basics of asymptotic analysis. So I want this course to be accessible to even undergraduate students, or it's quite senior undergraduate students, and then junior graduate students who may not necessarily have a background in asymptotic analysis. A lot of you might have had courses, either ad hoc or formal courses in asymptotic analysis, so a lot of this background material will be familiar to you, but I think it's good review, and in any case, we might have some new perspectives about some of the things you might have picked up as undergraduate students or in some of your graduate level courses. Okay, so let's start off with just a quick review of what we looked at last time. I introduced you to this crystal growth problem, and we explained that this is a nonlinear differential equation motivated by a geometric model for crystal growth, and epsilon here is a regularization parameter that's supposed to be small. And we derived asymptotics for this problem, so approximations at leading order and at next order, and then we came to the surprising fact that in fact this problem has no solutions. We looked at it numerically, solving from minus infinity, where the solution should be minus pi by 2, to positive infinity, where the solution should be pi by 2, and we found that at this value of epsilon 0.01, you develop these ripples in the far field that contaminate the solution at positive infinity, and so it seems from this numerical solution that there does not seem to be a solution that satisfies the two necessary boundary conditions of it being flat upstream and downstream. And then I explained to you that it turns out that these oscillations are in fact exponentially small in epsilon, and then we looked at some of the consequences of this. So we talked about series divergence. We talked about how exponentially small things are not necessarily negligible, and they can be very relevant. They can be very relevant because they capture some interesting physical effect that you want to know more about, or in this case, they can be relevant because they can separate a solution from existence and non-existence, or rather a problem from having solutions or not having solutions. Okay, so the lecture today is, again, we're just going to go through the basics of asymptotic approximations. I'm going to assume that most of you don't have a background in asymptotics. We're going to build up some of that background. We're going to do some more basic problems in matched asymptotics and integral approximations. in the next few lectures. And then finally, once we have enough of that core background, we're going to return back to these more specialized problems and then see whether we can resolve them. So let's first talk about convergence and divergence. And in the last lecture, I briefly mentioned the fact that historically this was one of the big interesting paradoxes in mathematics, almost equivalent, on equal footing to the discovery of non-Euclidean geometry. The idea that, or rather the paradox of using divergent series that add up to infinity, or series that don't converge in order to describe phenomena that you believe is well behaved. And this presents us with two interesting perspectives about convergence and divergence. The classic one of the Frenchman Niels Abel that I talked about last lecture. Divergent series are the invention of the devil, and it's shameful to base on them any demonstration whatsoever. Right? The kind of the pure mathematician's view, and then somewhat humorously contrasted with the applied mathematician's view. Divergent series converge faster than convergent series because they don't have to converge, right? And so this is a bit tongue-in-cheek, but it actually does capture this kind of historical paradox of using divergent series, where the practitioners, in particular in the 1800s, they were the astronomers who were using these series approximations. They knew that already from the first term, you would often get an excellent approximation, and then if you took a few more terms, it would converge, and the approximations would get even better. In a lot of the problems at the time, these celestial mechanical problems, you couldn't even go to that many terms in the approximations. You would never even really see that it diverges. And if any of you use asymptotics in your own research, or you've encountered perturbation theory, you would know that usually you don't go past the first, second, third term, because algebraically it can get extremely difficult and it's somewhat unnecessary as well. Okay, but what we want to do is I want to introduce you to a classic contrast between convergence and divergence in terms of this error function integral. Okay, so we're going to look at the convergent perspective and look at the divergent perspective and see that in fact convergence theories are probably not as useful as traditionally they're made out to be in the undergraduate curriculum, right? When we teach undergraduate mathematics, we always start with definitions of convergence, and this is one of the first things you learn in analysis, and then you find out that actually convergent series are probably not as useful as divergent series. So why is that? And can we give an example of that? And the answer is yes, we can. We're just going to look at this this error function integral. Okay. So the ERF function, or this error function integral function, or special function, is an integral from 0 to z of the Gaussian e to the minus t squared dt. Okay, and so we think, right, you're just integrating a Gaussian from 0 to a point z. For concreteness, let's just take z to be real for now, and though there might be some interesting questions that you might want to think about if z is complex. And this is a function that's highly humped at 0, so it makes sense for us to try to expand the exponential into a Taylor series about t is equal to 0. So in the first method, that's what we're going to do. We're going to write ERF as integral from 0 to z of 1 minus t squared plus t to the 4 over 0, 1, 2 factorial plus dot dot dot. Okay, so that's very straightforward, and then you just integrate things as usual. So this is z minus 1/3 z cubed plus 1/10 z to the 5. And the next term is z to the 7, or 42, etc. Okay? And if we want, we can write down the full representation. So that's 2 over root pi, an infinite sum from n is equal to 0 to infinity of minus 1 to the n z to the 2n plus 1 over 2n plus 1 n factorial. Okay. So you can apply your ratio to test to that function, but that is a convergent function. The factorial grows to be quite large in the denominator, and then it kind of doesn't matter how big of a z you put in here, though it works better when z is near 0, as you would imagine. This eventually wins in the denominator, and the series converges. So this is, you would teach this in your courses as a very well behaved function. Okay, so this is convergent for all values of z. Okay, but what we want to try doing now is we want to put in a different representation of this integral, and we know that the Gaussian, in particular, we want to study the limit where z is large, where we know that the Gaussian e to the minus t squared integrated from 0 to infinity has a well-defined value of root pi over 2. Right? So let's now do a different representation for this function. Okay, so the trick is that you know that the value at infinity is just a finite number. By the way, I'm missing a factor of 2 of root pi. You would have seen a root pi factor that comes up there, so I forgot to write it down earlier. And so I'm going to go all the way to infinity, and then I'm just going to subtract the element from z to infinity to get that integral, and then I put in e to the minus t squared dt. And as I said, the integral from 0 to infinity of the Gaussian is root pi over 2, so the leading term here will just cancel these factors on the left here, and you'll get 1 minus that value. So this will be 1 minus 2 over root pi, and then an integral from z to infinity. Now, in order for you to integrate this thing here, right, when z is large, you want to make sure that you go up in inverse powers of t. So you're just going to do a little trick here to convert this into a form where you can do integration by parts. So if I write this as d dt of e to the minus t squared, then I need a factor of minus 2t, so I can just write 1 over 2t here. And then this is dv dt, and there's your u. So basically, you're going to get 1 minus 2 over root pi, and then in brackets, u times v, so that's minus 1 over 2t. That's e to the minus t squared from z to infinity. And then I think it's a plus z to infinity. You need the derivative of that one there, so that's 1 over 2t squared. And then again, e to the minus t squared dt. And so if you've done this right, then the point is that you're going to develop a series in inverse powers of t as you go further and further to the right there. Just keep on doing that trick of writing this as the derivative of something. And then this factor here, the infinity disappears, and you're left with 1 over 2z times e to the minus z squared. All right? So in total, if you keep on going, you're going to have 1 minus e to the minus z squared over root pi times z. And then in brackets, 1 minus 1 over 2z squared plus 1 times 3 over 2z squared squared plus 1 times 3 times 5 over 2z squared to the power of 3. This is a minus, and so forth, and so on. Okay? And I can simplify this into a single expression if I like. I'll write that up here. So this is 1 minus e to the minus z squared over 2, z squared over root pi times z times an infinite sum from 0 to infinity of minus 1 to the n 2n minus 1. Sometimes, if you've seen this notation before, that's what a double factorial is if it goes down in steps of 2 instead of steps of 1. And then this is over 2z squared to the n. Okay? So the point of this is that, so the point is that you should be putting in a value, or you think of putting in a value of z which is quite large, because this is an asymptotic expansion in inverse powers of z. So, but no matter how large of a value of z you put in, when you evaluate this thing to the nth power, when n is large, this thing will indeed be a large number to a large number, but then the factorial growth on the top will kill you, and this one will diverge. So you can verify this, and you put it into your calculator or so forth, put in the value of z here. You'll notice that the numerator will always win in this, and that the series will diverge as n goes to infinity. So this is in fact a series which diverges for all values of z. So the way that we would teach, our undergraduates is that this is a bad series. So this is divergent for all z with a 0 radius of convergence. Right? So we have this example now of a convergent series and a divergent series. Traditionally, we think of the convergent series as being a good thing and divergent series as being a bad thing. But then now let's look at an actual numerical evaluation of this problem. Okay, so what you're seeing here in this graph is I've chosen a value of z at z is equal to 5. And what I'm plotting on the vertical axis is the error. So I take the exact value of the error function that I might get from a numerical integration, say, and then I subtract out a series approximation of that exact value. And on the horizontal axis, what you see is the number of terms that I'm going to keep in my expansion. So the point is that if it's a convergent approximation, the error should decrease. It should get increasingly better and better the more terms you take, right? And the blue that you see is the convergent series approximation, whereas the orange is the divergent series approximation. So you see that at this value of z, at z is equal to 5, the convergent series starts with an error of 1 at the first term, which makes sense because the integral over the entire interval is root pi over 2 times 2 over root pi. So that's why there's an error of 1 for the convergent series. It diverges, the blue graph diverges, and at n is equal to 20, in fact, you have an error of 10 to the 8. You're 10 to the 8 off until it finally converges at 80 terms. You can see you're getting an error of 10 to the minus 10, around 10 to the minus 10. But in contrast, the divergent series, already at the first term, it has an error which is less than 10 to the minus 10. It gets better and better and better until it reaches its minimum point at n is equal to, say, 25 or so forth, and then it diverges after. So in practice, you would never use the convergence series because you don't want to be handling terms of order 10 to the 8, in fact, in your arithmetic. And you would just use the divergence series. And this, of course, gets better as z increases, right? But even for z is equal to 1, the divergence series gives a very good approximation of this integral. So this is an example of the fact that convergence theories are perhaps not as useful as we teach it to be in some of the early courses, and as George Carrier wrote, divergence theories converge faster than convergence theories because they don't have to converge. Okay, so it's worth keeping in mind that this property of a asymptotic expansion going down to a minimum point and then diverging afterwards was known at the point of the 1800s. And mathematicians knew that this is, they had an understanding that this is one of the reasons why divergence theories are useful in practice, but it was never really clarified. And that's why there was a trend to spurn them away. Okay, so we've looked at this example of convergence and divergence, and I've given you an example as according to this error function, and also so one of the questions is, would you respond to an undergraduate student who says they're having difficulty understanding Biot orders asymptotics of nonlinear PDEs? I think that would be a very advanced undergraduate student, so I don't need to respond to that. It sounds like the undergraduate student has things under control. Okay, so I want to go on now to Poincare and to give you precise definitions of what it means to be an asymptotic approximation. So where we left off with the history last time was that in the late 1800s, so as I indicated, there was a lot of mathematicians and physicists and practical applied scientists who were using divergence theories quite successfully in order to develop approximations. But there was a trend in the early to mid 1800s to turn away from them because divergence theories are the invention of the devil. Then in the 1880s, these two works, primarily by Stiltes and Henri Poincare, tried to develop a more rigorous theory of what it meant for a series to be asymptotic. And Poincare now today is known as coming up with the definition of an asymptotic approximation. That's what we're going to present today. These contributions were made primarily through these three large manuscripts that he wrote in Part 1, Part 2, Part 3, these new methods of celestial mechanics to address this n-body problem, the problem of trying to understand the orbits of n point masses and modeling the planets. And what's interesting that I wanted to point out was that unlike a lot of pure mathematicians, Henri Poincare was actually very respectful of the use of divergence theories in science and in mathematics, right? He wasn't saying you shouldn't be using them. He was saying that actually they seem to be very powerful and we need to have a better understanding of why they're useful. So he wrote, between mathematicians and astronomers, some misunderstandings exist with respect to the meaning of the term convergence. Mathematicians who are mainly concerned with perfect rigorousness of the calculation and frequently are indifferent to enormous length of some calculation which they consider useful without actually thinking about performing efficiently, stipulate that a series is convergent if the sum of the terms tends to a predetermined limit, even if the first terms decrease very slowly. Conversely, astronomers are in the habit of saying that a series converges whenever the first 20 terms, for example, decrease rapidly, even if the following terms increase indefinitely. So this is what I meant about his respectful nature of convergence and divergence. He was pointing out that phenomena that we saw earlier in the error function. And this is the example he says. Let's take this example. Let's consider two series that have the following general term. So this first one is 1,000 to the n over n factorial. And then the second one is n factorial over 1,000 to the n. He said pure mathematicians would say that the first series converges, even that it converges rapidly, since the millionth term is much smaller than the 999/909th. However, they will consider the second series to be divergent, since the general term is able to grow beyond all bounds. Conversely, astronomers would consider the first series to be divergent, since the first 1,000 terms increase. They would call the second series convergent, since the first 1,000 terms decrease, and since this decrease is rapid at first. Both rules are legitimate, the first for theoretical research and the second for numerical applications. Both must prevail, but in the two entirely separate domains of which the boundaries must be accurately defined. So I think this is very interesting, and you contrast this with the perspective of Niels Abel and divergent series are the invention of the devil. Okay, so he had a number of works around this period, around the late 1880s, leading to these three volumes on celestial mechanics. And it's really interesting. I mean, I have the books, here, and if you ever get the chance, though it can be hard to get a copy of these books. They're very interesting, mainly because when you read the books, you realize that what Henri Poincaré wrote in those books essentially became undergraduate teaching for dynamical systems. So when you go through your dynamical systems and the way that we teach differential equations, a lot of that is inspired by the developments that he did in these books. So he had an earlier work in 1886 that eventually also led to some of these later large manuscripts. And in these works, as it pertains to asymptotic expansions, he did a few things. So one of the key things he did was that he formulated a clear definition of an asymptotic approximation of a function. He demonstrated that the typical asymptotic approximations, which were used in celestial mechanics, these what are now called Poincaré-Lindstedt series, was in fact divergent. And then he demonstrated that there is a kind of an arithmetic, a calculus of asymptotic approximations. In particular, you can add two asymptotic approximations together and they remain an asymptotic approximation. You can multiply or divide them as long as you don't divide by 0, and you can also integrate them, but you can't differentiate them. And then he demonstrated that he took essentially linear variable coefficient differential equations, systems of linear differential equations, and then showed that if this system has linearly independent solutions, the usual division into linearly independent solutions, then these linearly independent solutions are described by divergent approximations. So the point is that the point that people were hung up on was if you develop a divergent asymptotic approximation to a problem, how can you be sure that this is a solution of the problem? Because obviously it does not make sense to add together something that is infinity, even though it can give you very sensible approximations. And we encountered an example of that in the crystal growth problem. We happily developed an asymptotic approximation, only later to be told, well, actually, there is no solution to that problem. And so what Poincaré demonstrated is that if there are, in the case of these linear problems, there are linearly independent solutions of the problems, then the approximations that you develop must be asymptotic approximations of those solutions. Okay, so and then finally, the point is that after this 1880s period, he kind of brought back the research into asymptotics. And we were much happier now to work with divergent series once Poincaré had kind of established this baseline foundation. Even though I say this for analysts, but because during this period from the 1800s, there were plenty of applied mathematicians and plenty of physicists who were continuing to use these asymptotics very happily and very successfully. So this is really a discussion about mathematical analysis. Okay. One thing I want to mention, but we're going to revisit, is that in the graph that I presented to you before of the exponential of the error function, so the point is that you have a graph of number of terms n that you're going to keep, and then the error. So this is basically the exact value of the function, if you want to write f of epsilon here, minus the asymptotic approximation or the convergence series that you truncate at n terms. So maybe n minus 1 here if I want to truncate at n terms, including 0. And this is fn. Then typically the behavior that you get is like that. It's a somewhat universal behavior where it converges rapidly. And then this point here that we're going to revisit often is called the optimal truncation point. And heuristically, at least for now, but we will justify this a bit more in detail, this optimal truncation point is roughly where the magnitude of adjacent terms are equal in the asymptotic approximation. So there is a heuristic of developing this point, and you would think that this point pragmatically is telling you that that's the point where you should truncate the approximation because you're going to get the best error right before it explodes afterwards. The other thing I'll mention is that the other property of asymptotic approximations is that this error here, so you fix your value of epsilon for this error. Let's say I fix it at 0.1. The point is that if I decrease the value of epsilon, so let's say I decrease it to 0.01, then the whole curve shifts towards the right. The truncation happens later in n, right? And this is the asymptotic property. The approximation gets better and better if I take epsilon to 0, but it diverges if I fix epsilon and I take n to infinity. And this was the thing that Poincaré had attempted or had clarified, this property of being asymptotic. Okay, so in the next little while, in what remains of this lecture, I want to go through just the basic definitions of things like the notation, what this tilde means when you write squiggles here, or tilde, what much greater than means, much less than, big O notation, and then finally a definition of an asymptotic approximation. It's worth saying that in this course, we don't really, well, we don't prove anything. So we do a lot of formal computation. It's important for you to know that there is this definition of being asymptotic, but you rarely have to work with it directly, right? And that's kind of the great power of asymptotics is a lot of it is intuitive. Okay. Now, before I start, I want to just clarify the typical scope of asymptotic problems that we work with in this course. So typically, we're going to consider asymptotic approximations for a function y, say, and in this course, we mainly deal with what are called parametric asymptotic approximations. So they typically will depend upon a domain variable x and then a small parameter I'll call semicolon epsilon here, and typically epsilon tending to 0. Or I can have a parameter which also tends to infinity. Okay? And I think of this problem as being governed usually by a differential equation or by an integral equation or a partial differential equation, etc. Okay, and the other way of doing it is to do non-parametric asymptotic approximations where you don't have a domain parameter and it's just y as a function of a parameter which tends to 0 or which tends to infinity. But usually for this course, we think of a function like this, and it might be governed by an ODE or a PDE or an integral equation, etc. So that's the kind of problems that we consider. Okay. The other phrase or terminology that I'm going to often use is regular versus singular asymptotic approximation. So a very simple example of this is that if I want to develop the roots to to an equation, so suppose I want to solve either, let's say, epsilon times x squared plus x minus 1 equal to 0, I want to develop a power series expansion of x in powers of epsilon for this series versus if I have, let's say, x squared plus epsilon times x minus 1 equal to 0. Versus if I want to solve this polynomial equation. And so for this problem here, we would call this one a singular perturbative problem, because the point is that the behavior at epsilon is equal to 0 somehow fundamentally differs from the behavior when epsilon is not 0. In particular, in this case, the epsilon is 0, you don't have a quadratic. And when epsilon is not 0, you have a quadratic. So epsilon can be infinitesimally small, and I have two roots. But if it's 0, I have one root. Whereas for this problem, I always have two complex roots, regardless of how small epsilon is. So this is what's called a regular problem, and then this is called a singular problem. And the same situation occurs for differential equations. I can have a differential equation like this, say, versus I can have a differential equation like this. And again, the point is that this is a singular perturbative problem because when epsilon is 0, you've fundamentally changed the structure of your solution. Whereas in this one, if epsilon is 0, you still have two linearly independent solutions to this second order problem, right? And the kind of the basic the basic punchline is that most of the interesting problems, most of the cool problems in asymptotic analysis involve singular perturbative phenomena. You can have singular perturbative phenomena without multiplying the highest derivative for things like multi-scale problems that we might or might not see later. But this is an important distinction between regular and singular problems. And for the most part, the only thing you have to keep in mind is that it's singular if the behavior at epsilon is equal to 0 is very different from the behavior when epsilon is not 0. Okay, so I've kind of limited the class of problems that I'm interested in, and then now I want to just introduce you to some of the terminology so we're all on the same page. Okay, so I want to introduce you to the tilde notation, the much less than or much greater than notation, big O and little o notation, just define what it means to be an asymptotic sequence and define what it means to be an asymptotic approximation according to Poincaré. And I've already done a little bit of discussion of the difference between a singular perturbative problem and a regular perturbative problem. Okay. Okay, so let's see. So let's start with some definitions. I should say that the notes for this lecture, I should put it online once I get my act together. and then you'll be able to find it at some location. So I'm just going to define what it means to be this tilde, or asymptotically equivalent. So given a function f of epsilon and g of epsilon, you would say that we say that f of epsilon twiddles g of epsilon, or is asymptotically equivalent, if the limit is the same. So if the limit as epsilon tends to 0 of f of epsilon over g of epsilon is 1. Okay, so it's a bit unusual to make these definitions as a function of epsilon. Usually if you're being taught this subject for the first time, you'll usually say like f of x is twiddles g of x in the limit that epsilon tends to 0. So sorry, let me just read this over again. F and g, so given a function f and g, we say that f twiddles g of f of epsilon twiddles g of epsilon as epsilon goes to 0. You always have to specify the limit. We say or it's asymptotically equivalent. We say it's asymptotically equivalent if this is true. So as an example, I don't know, take f of x to be f of epsilon to be sine epsilon, and take g of epsilon to be epsilon, say. So they both look like a line as epsilon tends to 0 of gradient 1, line of gradient 1. Okay, so that's what we mean by twiddles. The next thing I want to introduce you to is big O notation. So I guess if you're discussing this with another mathematician, you would say twiddles, or sometimes you say behaves like, is asymptotic to, right? So that's kind of how you would describe that symbol. And then the next one is big O. Okay, so we say that f of epsilon is at most order g of epsilon as epsilon tends to 0, or you would write that as f of epsilon is equal to big O of g of epsilon. My epsilons look a bit like t's. If in the limit this is less than some m. Okay, so the point, I mean, the way I think of it is that if you want to be using twiddles, you had better get the prefactor right, the number in front right, whereas when you deal with an order notation, you don't have to get that number right. So, for example, f of epsilon is sine of epsilon. Let's do sine of 2 epsilon is of order epsilon, as epsilon tends to 0. Because that ratio then is less than 2. Okay, so the point is that this big O captures the kind of power law behavior of the function. Whereas if you want to write twiddles, then you would have to make sure that the prefactor is exactly 1. Okay? Okay, so that's a big O, and then you also have little o, which, and then you have much greater than and much less than. Again, as I said, a lot of these definitions you almost never use once you kind of understand how to handle asymptotic approximations. because they're quite intuitive. So the next definition is little o, and then this symbol here, which we call much greater than, and then this symbol here, which we call much less than. Okay, so we write that f of epsilon is little o g of epsilon as epsilon goes to 0 if the ratio between epsilon or g of epsilon basically tends to 0 in that limit. So the numerator goes to 0 much faster than the denominator. It's little o g of epsilon. And in this case, we would also write that f of epsilon is much less than g of epsilon. Again, in that limit of epsilon tending to 0. And then there's an equivalent definition for g much greater than f. Okay? So again, most of these will be intuitive because when you deal with asymptotic approximations, you're just often balancing orders of epsilon, and then the progression is quite clear. And so in the limit that epsilon goes to 0, epsilon's cube will be much less than epsilon squared, and similarly. Okay? And so then the last thing is to introduce you to what it means to be a asymptotic sequence, followed by what it means to be an asymptotic approximation. And this is the Poincaré definition. Asymptotic sequence. Okay, so a sequence, and let's index it by delta n of epsilon. Let's go through the natural numbers, or sorry, the positive integers, is said to be an asymptotic, to be an asymptotic sequence if basically delta n plus 1 is always much less than delta n for all n greater than 0, for n all greater than or equal to 0. So basically the progression just gets smaller and smaller. So i.e., your technical definition just says that delta n plus 1 over delta of n of epsilon tends to 0 as epsilon tends to 0. Okay. So most of the sequences that we deal with are super simple. They're just algebraic progressions in powers of epsilon, but you don't have to have that. You could have much more exotic asymptotic approximations where the sequence that you're dealing with, it can be even transcendental numbers, epsilon to a transcendental power, and then multiples of that, or it can involve logs, so it can be much more exotic. But for the most part, the asymptotic sequence that you might have in your head is the standard one, which is just in algebraic increasing powers of epsilon. Once you have an asymptotic sequence, then you can define what an asymptotic approximation is. Or asymptotic expansion. So if we let delta n of epsilon be an asymptotic sequence, let's construct a series. So we're going to use that sequence to construct a series. Let's take fn of epsilon to be some an times delta n of epsilon, where an is constant. And let's construct a series. So we're going to call, should I give it a name? No, I think I'm just going to call it a series of fn of epsilon from n is equal to 0 to infinity. I'm going to mention about that upper limit in a second. Okay, so this is an asymptotic approximation or expansion of a function. Let's say f of epsilon is the true function. This always has to be given in terms of a limit, so you're always taking some limit of epsilon tending to 0. If for all n greater than 1, basically the ratio of the true value minus your approximated value. So let me take n terms from my series. This is the thing that we were plotting before, and then I divide that by the last term. If this thing tends to 0 as epsilon tends to 0. Okay? So that is the definition of an asymptotic expansion, one in which, so this quantity here is essentially the remainder. It's the exact value, well, it's the function that you're trying to approximate minus the n-term approximation. That's the remainder. And the point is that the remainder is much less than the first term that you have truncated at. Okay, so if I write that in words, it's an asymptotic approximation if, so this is just a note, so the remainder is r, I think I've called it Rn of x here, so this remainder is this thing here. And this is equivalent to the fact that the remainder is much less than fm minus 1 of epsilon. So the remainder is much less than the last term that you've included in your approximation. Okay. So this is basically the last bit of today's lecture, is just to introduce you to this notation for twiddles, for much greater than, much less than, for big O. And you might have encountered this formally in some of the courses that you've taken in asymptotics, or you might have encountered it informally just because you're used to manipulating asymptotic approximations. As I said, we won't typically work with these definitions, though you can if you want to. And the last thing I'll mention here is that as we said previously, Poincaré had noted that if I have two asymptotic approximations, I can multiply them and I still have an asymptotic approximation. I can add them together and I have an asymptotic approximation, and I can integrate them, but I just can't differentiate them. A good example of a function that you can't differentiate is, for example, if I think of differentiating epsilon times cosine of 1 over epsilon. Okay, and the point is that when you differentiate it in this way, you may be destroying the well-ordered property of the function. In this case, you end up with powers of 1 over epsilon because of that derivative. The other thing to mention is that you can have multiple asymptotic approximations. So asymptotic approximations of a function are not unique, and we'll give you an example of that in the next lecture. But primarily, the next few lectures is about reviewing some of the techniques in asymptotics that we're going to need to know as we go into the more advanced asymptotic section. So we're going to talk about things like boundary layer theory. How do I solve two-point boundary value problems in ODEs? And we're also going to talk about, we're going to need to know some knowledge about integral approximations, because the primary mechanism for studying some of the more complicated problems is to work with an integral equation rather than a differential equation, just as Stokes and Stieltjes had done. We're going to look through some classic analysis of integral equations and develop the asymptotics there. But that's it for today's lecture. Thank you for coming by, and I'll see you in the next one. Thanks, everyone.